All right, we're on day 23, and we were just going through a hypothesis test. We were about to step 4. I want to back up just a little bit because what we're looking at is calculating our test statistic and writing our probability statement in step 4. And I just want to go over just building up. I want you to see some similarities in what we've been doing and what we're doing now. So what we've been doing is hypothesis testing, and every time you do a hypothesis test, you need to come up with what's called a test statistic, okay? And the test statistic, the general formula, and this is on the AP test, is your observed value okay, this is from your sample, or samples, plural, minus the hypothesized value. That is the value in your null hypothesis, divided by the standard error, standard deviation, of your statistic. So whatever your statistic is, if it's a mean, then this would be the formula for the standard deviation of the sample mean. If it's a difference of means, then this is the standard error of a difference of means. So what we had been doing, this is back in chapter 23, so chapter 23, hypothesis test for a single mean, we would have had our probability statement be the probability that our mean is less than some sample value. This is your observed value. Okay, that same one that's going to go here in your formula. And you translate that into a t-value. When you're dealing with means, you use the t-distribution. So t is less than. Now, the way you calculated your sample statistic was your sample mean minus the hypothesized mean divided by s over the square root of n. Okay, and then you did your t, you had to come up with your number of degrees of freedom. And then you did your TCDF, and then your lower bound, your upper bound, and your degrees of freedom for your t distribution. So what we're going to be doing today, chapter 24, okay, we're doing a difference of means. So our probability question, okay, and then that gave you your p-value, which you then, backing up. In chapter 23, you did the probability that the mean is less than whatever your observed value is, or it could be greater than, it just depends on your null or alternative hypothesis. Then you calculated your test statistic, and then you did the TCDF, lower bound, upper bound degrees of freedom to get your p-value, then you compare it to alpha, and then make your decision. All right, so now in chapter 24, we're doing a similar thing, except instead of having a single mean, we have the difference of two means. What is the probability that mean 1 minus mean 2 is less than a certain value? It could be greater than a certain value. And that is the probability that t, now you're going to find the t value, the test statistic, for the difference of means. So that is your sample difference, okay, which would be x bar 1 minus x bar 2, minus the hypothesized difference, mu 1 minus mu 2, and a lot of times that is 0, divided by the standard deviation of this statistic, which is the square root of the standard deviation of the first sample squared divided by n in the first sample, plus the standard deviation of the second sample squared, or the variance, divided by n of the second sample. Okay, then you're going to do, to work that out, you need to come up with the degrees of freedom, which is kind of a messy formula. And then you're going to do the TCDF, and then lower bound, upper bound, and then your degrees of freedom. You're going to get your p-value, and you're going to compare it to alpha. So it's the same process, we just have a different calculation each time, depending upon what we're doing for our sample. So now if we go back over to this page, we were on step 4. We already talked about that there was a difference, a positive difference between these two. And so we thought that that fish oil was better than regular oil, but that could have been due to randomization variability. We wrote our hypotheses, we checked our conditions. Since our sample size was small, we had to do the normal probability plots. We have to graph each of them and state that they're roughly linear. That's very roughly linear to me. You know, I suppose you could say roughly linear. And so we could say that they're from normal populations. Now we're going to calculate our p-value. Now this is slightly different. Now our t, we just talked about, is the observed difference minus the expected difference. So this will be the observed difference, x bar 1 minus x bar 2, minus the expected difference, mu 1 minus mu 2. So here it is, look, they put it right here. And then the standard error of the difference, the same thing we just wrote on the other page. That is the test statistic we're going to calculate. Now, the degrees of freedom looks like this. That's pretty ugly, isn't it? That's the formula for the degrees of freedom for a difference of means. All right, so our probability statement, we would say what's the probability that the difference in the fish oil and the regular oil is greater than 7.71. We do our calculation of our test statistics, so 7.71 was our sample difference, minus our hypothesized difference, which is 0, meaning they do the same thing, and then the standard deviation of our first sample, which you can calculate. You just put the samples into list 1 and list 2. If you were going to make this, you just make sure both of your samples are in list 1 and list 2. And you can do the one variable stats to get each of the standard deviations. So the standard deviation of the first sample squared divided by 7 plus the standard deviation of the second sample squared divided by 7, add them, square root of that whole thing. That gives you your test statistic of 3.06. So now what we'd want to do is TCDF. We'd want to type in our lower bound and our upper bound and then our degrees of freedom. So our lower bound is 3.06. And greater than means we're going to go to infinity, 9999, but we have a big question mark on our degrees of freedom because I really don't feel like calculating that. Really, I don't, and I'm pretty sure you don't either. So we have two options at this point, neither of which is calculating the degrees of freedom by hand with the formula above. So what we can do, first of all, and we're going to do this first, and then we're going to do number 2, just so you can see how both of them work. Use the conservative estimate for degrees of freedom, which is the smaller of n-1 and n-2. So this gives the test less power. All right, so that's the first thing we're going to do. So n-1, the first one, 7 minus 1 and 7 minus 1. So I'm going to use 6 degrees of freedom. The smaller, they're both 6. So I'm going to use 6 degrees of freedom and get the p-value. So I'm going to go second distribution. I'm going to do my TCDF. My lower bound is 3.06. My upper bound is a bunch of 9s. My degrees of freedom is 6. And it gives me that my p-value, so my p-value is 0.0111. My alpha level was 0.05. All right. So this is less than, and when the p-value is less than alpha, we reject the null. Okay, we would reject the null. We would say that, well, there is evidence that fish oil is better than regular oil at lowering diastolic blood pressure. All right, so the second option, how could I do this? We can just use the test menu. There is a test. Go to your test menu, which is above the math. So second math will give you, whoops, that's not right. Second distribution, no. Oh, just to stat. So stat, go over to test, sorry. That took me a little bit too long. So test menu, hit stat, and then go over to test. And then we want to look down at test. It might be 4, it might be different. It's a 2-sample t-test that you're looking for. So there's my 2-sample t-test. And this is really nice. So I can input the data. Okay, I can input the data. And that means I better put my list 1, my data in list 1 and list 2. And leave your frequency as 1 and 2. And then this allows you to select your alternative hypothesis. So if we look at our alternative hypothesis, it was greater than it's going to be greater than, so that is the one that we would select. And then it's not pooled here, and then we want to calculate it, but here's the deal. I need to make sure that I put these data in my list 1 and list 2, so I'm going to have to back up to the first page, and we're going to have to put our data in list 1 and list 2. So I'm going to go to Stat Edit, and then in list 1, actually this one doesn't have a list 1, so mine are going to be in list 2 and list 3. So in list 1 I put 8, 12, 10, 14, 2, 0, 0. And then in list 2 I put -6, 0, 1, oops, 1, 2, -3, -4, 2. Alright, so then I'm going to go back to Stat Tests 4, and I have my data. It's in list, mine is in list 2 and list 3, and it's greater than, and pooled no. I want to calculate, and it calculated it. Now notice, if we go and look at the page that we were just on, what I want you to notice is that this T is the same as the one that is here, that we calculated by hand. The p-value this time is 0.0065. So when we do it using method 2, we get a p-value of 0.0065 with a degrees of freedom of 9.26. And yes, you need to write that. Up here, our degrees of freedom was 6. So that's why you really need to let them know the degrees of freedom. You have to put that down, because you can choose to use the conservative or use your calculator, which is so easy. And it gave you the p-value, and you compare that to alpha of 0.05, which is still less than alpha. So you're still going to reject the null and make a conclusion that fish oil does appear to be better than regular oil at lowering diastolic blood pressure. So the tests on this page using the conservative estimate, this is what you type in, and you get a p-value of 0.0111, which we did, and using the test menu, you get the p-value of 0.0065 with 9.26 degrees of freedom. And since the p-value is less than alpha, we do reject the null and conclude that fish oil is better than regular oil for reducing blood pressure. Alright, so now we have another example here that's already walked through for us, so I'm going to move through it kind of fast so we don't have to start another video. So each person in a random sample of 228 male teenagers and a random sample of 306 female teenagers, there's N1 and there's N2, was asked how many hours he or she spent online in a typical week. Based on the summary statistics below, we can conclude there is a significant difference in the mean number of hours online per week for the two genders. So the females had a mean of 14.1 hours and the males a mean of 15.1 hours, and here are their standard deviations. So at first glance it does appear, when you take the mean of females minus the mean of males, so 14.1 minus 15.1, you get -1. So it does appear that there is a difference of -1, meaning females spend less time online than males. But it's possible that in reality the genders spend the same amount of time online, and the difference we observed is due to sampling variability in this case. And we're going to do a 2-sample t-test for the difference of means. So here's our null and alternative hypothesis. Our null is that the difference is equal to 0, and in this case it's not equal to 0. So this is a 2-sided test. And remember, with our 2-sided test, we need to multiply our probability by 2, because we need to know the high end and the low end, because it could be up, high, or low. The conditions are checked. Are they independent samples? Yes. Is each sample less than 10% of all teenagers? Yes. And large sample sizes, both are greater than 30. So then our p-value was twice the probability that their difference is less than -1. So twice the probability that t is less than -1 minus 0 over the calculation of the standard deviation. From here you just put this into your test statistic, and this time you do it through data. So the data, this time you do it through stats, so you hit the stats and hit enter, And then you're going to type in X bar 1, the mean is 14.1, and the standard deviation is 11.8, and then the mean of the second one is 15.1 and 11.4, and, whoops, sorry, we have to go back up. N of the first one was 228, and